Hi all, here is the last topic in module 5, that is Reed-Solomon codes or RS codes. RS codes or Reed-Solomon codes is a subclass of non-binary BCH codes. Okay, so far we have discussed about binary codes. So Reed-Solomon codes are non-binary codes. Okay. The encoder operates on multiple bits rather than individual bits in binary encoder. That is, in a binary encoder, the encoder operates on individual bits, as we have seen in case of linear block codes, cyclic codes, and BCH codes. The encoder operates on individual bits. But in case of this non-binary Reed-Solomon codes, the encoder operates on multiple bits at a time. Okay. Or we can say it will take a block of bits as a symbol and it will operate on that particular block of bits, or we can say multiple bits. Then main parameters of Reed-Solomon codes. For a T error correcting Reed-Solomon codes has the properties block length n equal to 2 raised to m minus 1. Actually, this m value എന്ന് പറയുന്നത് നമ്മുടെ മൾട്ടിപ്പിൾ ബിറ്റ്സിലാണ് ഓപ്പറേറ്റ് ചെയ്തതെന്ന് പറഞ്ഞല്ലോ. അപ്പോൾ ഒരു സിമ്പല് മൾട്ടിപ്പിൾ ബിറ്റ്സ് ആയിട്ടാണ് റെപ്രസെൻറ്റ് ചെയ്യുന്നത്. ആ ഈച്ച് സിമ്പലിലുള്ള നമ്പർ ഓഫ് ബിറ്റ്സ് ആണ് ആക്ച്വലി എം എന്ന് പറയുന്നത്. ഓക്കെ, സോ ബ്ലോക്ക് ലെങ്ത് എൻ ഇസ് ഈക്വൽ ടു 2 റൈസ് ടു m minus 1. മെസ്സേജ് സൈസ് is k symbols. Okay, then parity check size r is equal to n minus k, which will be equal to 2t symbols. And minimum distance d minimum equal to 2t plus 1 symbols. So you remember these parameters. Then coming to the encoding process, the encoder for an RSNK code on m bit symbols groups the incoming binary data stream into blocks each of k by m bits long. Okay, so consider a Reed-Solomon code, NK Reed-Solomon code. That means you will be having the block length n and number of message symbol equal to k. Then this encoder first groups the incoming binary data stream. So the incoming data will be binary stream. This encoder first groups this incoming binary data into um, blocks, that is each of k by m bits long. Okay, that is each block is treated as k symbols with each symbols having m bits. Okay, അപ്പോൾ ഓരോ സിമ്പിൾസിനെയും എം ബിറ്റ്സ് ഉള്ള ഗ്രൂപ്പ് സോറി ഓരോ ബിറ്റ് സ്ട്രീമിൽ എം ബിറ്റ്സിൻ്റെ ഗ്രൂപ്പിനെ എടുക്കും. ദാറ്റ് വിൽ ബി വൺ സിമ്പിൾ. ഓക്കെ, സോ ഈച്ച് ബ്ലോക്ക് കൺസിസ്റ്റ് ഓഫ് കെ സിമ്പിൾസ് വിത്ത് ഈച്ച് സിമ്പിൾ ഹാവിങ് എം ബിറ്റ്സ്. ഓക്കെ, അപ്പോൾ എം ബിറ്റ്സ് ഉള്ള കെ സിമ്പിൾസിൻ്റെ ബ്ലോക്സ്, അങ്ങനെയുള്ള ബ്ലോക്സ് ആയിട്ട് എൻകോഡർ ഇൻകമിങ് ഡാറ്റ സ്ട്രീംസിനെ ഡിവൈഡ് ചെയ്യും. Then encoding algorithm adds n minus k redundant symbols to a block of k symbols. Okay, so it deals with that group of symbols. For example, we can say if m equal to 8, we can say the symbols are bytes, right? Normally bits in a group of bits operate if our number of bits in each symbol equal to 8, we can say it operates on bytes, right? And that is an extremely powerful combination for its solvent. Then if m equal to 8, we can say each symbol is a byte, or each symbol consists of 8 bits. So in a block there will be k symbols of length 8. Okay, then to each symbol n minus k redundant symbols are added. Binary case bits redundant bits added here. To each block of k symbols are added with n minus k redundant symbols. Okay, so non-binary coding ആണ്. ബാക്കിയൊക്കെ BCHന്റെ almost same ആണ്. But since it is non-binary, this will operate on block of symbols. So each block consists of k symbols and each symbol consists of m bits. Okay, so that is the encoder for a Reed-Solomon code of NK code with m symbols. Okay, and another important property is for NK Reed-Solomon codes, the d minimum distance will be equal to n minus k plus 1. Actually, in all other linear block codes, this d minimum will be less than n minus k plus 1. Okay, in our linear block codes, this d minimum is less than n minus k plus 1. But for an NK Reed-Solomon codes, this d minimum will be equal to n minus k plus 1. That is, minimum distance is always equal to the design distance of the code. Such a code is called maximum distance separable code. This is an important property of Reed-Solomon code. This is a maximum distance separable code. That is, the minimum distance will be equal to the design distance of the code. Okay. So that's about Reed-Solomon codes. And let us see a simple example. That is, consider a 31-5 Reed-Solomon code. That is, our n equal to 31 and k is equal to 5. How many bits are there in a symbol of the code? What is the block length in bits? What is the minimum distance of the code? How many symbols in error can be corrected? Okay, so let us see the solution. Okay, so first question is, that is, we are given with a 31-5 Reed-Solomon codes. That means you have n is equal to 31 and k is equal to 15. That is, there will be 15 symbols and the block length is 31. Okay, and our first question was, how many bits are there in a symbol of the code? So how many bits are there in a symbol of the code? There are k symbols and the block length is 31. Then we can we have to find the number of bits in each symbol. So we have, so for question A, we have block length n is equal to what? 2 raised to m minus 1. Okay, so from this you can calculate the value of m. That is, how many bits are there in a symbol, that is m. Okay, so actually this m is the number of bits in a symbol. Okay, so I can write 2 raised to m minus 1 is equal to n, that is 31. Okay, or we can write, say, 2 raised to m is equal to 32. Then m will be equal to 5. Since 2 raised to 5 is equal to 32, we can write m is equal to 5. That is, we can say the number of bits per symbol. Number of bits per symbol is equal to 5. Okay, so that is the first question. And coming to the second question, what is the block length in bits? Block length in bits. Block length actually, we have 2 raised to m minus 1, that is in symbols. So in bits, what will be the block length? So we can say block length in bits. So we have total block length is equal to n, and each symbol consists of 5 bits, right? So you will be having n into 5 bits. That is 31 into 5, 155 bits. Then our next question is, what is the minimum distance of the code? So minimum distance of the code is actually given by minimum distance. By definition, we have d minimum is equal to 2t plus 1, right? But this t, we don't know the value of t. We can say another relationship was there, that is d minimum will be equal to n minus k plus 1 for this Reed-Solomon codes. So now from this we can calculate n is equal to 31, k is equal to 15 plus 1. So we can say minimum distance will be equal to 17. Right? Now next question is, how many symbols in error can be corrected? That is the t. Okay. So now we have to calculate the value of t, that is number of correctable symbols. That is t. You have to calculate t. So we have the relation d minimum is equal to 2t plus 1. And now we got the d minimum value, that is equal to 17. So using the relation, we can calculate t. 2t plus 1 is equal to 17. Then we will be having 2t is equal to 16 and t will be equal to 8. Okay. So we can correct 8 symbols which are in error using this particular Reed-Solomon code. Okay. So that's about Reed-Solomon codes.